Well, hello everyone again. Welcome to the first bootcamp and hackathon for this course. So this bootcamps basically help you navigate through your homeworks, both part ones and part two. So I'll quickly go through the homework one, part one, and then we will spend more time on the part two of this homework. Most of you might have already started, but so like homework one, part one, what we are like, what you have to do in this is basically implement neural network architectures using NumPy only. So you will be creating your own custom library, which we call as MyTorch, and which is like very similar to PyTorch. So basically, you will be creating all the functions like activation functions, loss functions, which are required in order to create a neural network architecture. And in homework 1P1, we will be creating MLPs, which is multi-layer perceptrons. And I guess Prof is currently have already started teaching on how multi-layer perceptrons work. So how to start working on homework 1P1? I would say go and read your write-ups. Write-ups is your friend in this. Like everything is in, it's completely and in detailed version written in your write-ups. As soon as you open your writers, you will see a checklist. And if you go and like follow this checklist properly, it will be a very smooth process and you can just complete one and each and everything properly. There are reference to lectures as well as to which lecture you should refer if you are facing any issues in particular part of the code. Moving on, as I said, this one is for this one we are talking about the multi-layer perceptrons, and as soon as you will download the code from the autolab, this will be the structure of it, wherein you will have the linear activation loss batch term functions, your HDD functions, and the models, the mlp.py file. This is how the most important part is the autograder. So some of you have been posting on the Piazza like how autograder works. So whenever you do any submission, you can locally test your autograder by posting by changing your flags. So there's an autograder.flag file in your handout itself. Just put it as true or false, whatever part of the code you want to test on. Okay. So I'll just give you a quick big picture as to what this homework is about. As we know, for any MLP, we need basically a linear layer, an activation layer, and a loss function. So you will be so starting from an input, you will be coding how linear layer will be calculating your affine function, affine value, and then your activation function will be applied on that affine value, and then it will bring that non-linearity to you to that affine value, and create the active and will give you the predicted value. Now on this predicted value and the actual output, the loss is calculated. This loss is then back propagated to the entire network, and this back propagation is done using gradients. So back propagation is something which will be covered in the future lectures by the prof more. But in order to give you more insights as to how can you navigate through this particular homework, there is one resource which we have shared in the Piazza as well. Yeah. So in the Piazza post itself, we have this computing derivatives post. Just read through this document. It's very well documented, and here you will find all the things which will help you identify how chain rule works, how you calculate the derivatives, and how to compute the derivatives for each and every sub part of the equation. Let's just go to the code, and I'll go show you how the code works, how the code looks like. So as I said, there is a models function, which is the mlp.py. This is the main MLP file where you'll be writing code for hidden layers 0, 1, and 4. So you'll be writing 3 MLP architectures. In this architecture, you will be calling the functions which are written inside your MyTorch and NN library, NN directory, which is activation, linear, and loss. These three functions will be called in the MLP file, and your batch norm and SGD are the extra functions which you'll be writing in order to understand how batch normalization works and how optimization can be done using stochastic gradient descent. So, for example, so firstly, as you see the activation function, we have given you an example of how to write an activation how to write an identity activation function. On the similar lines, you have to code it for the sigmoid, tanh, and relu. So basically, you will have a forward and the backward function inside this. And what will you implement in this? It's written in the writer code. Like so, this is how you navigate. Yeah. So here like for each and every activation function, like for sigmoid activation, this will be the forward equation, and similarly, so we have the forward equation and the backward equation, and that you have to code in there. Similarly for the linear functions, so if you go and here is the linear forward equations. So this particular linear forward equation you will need to be you'll code it in the linear.py file. So first you will initialize your weights and biases according to your shapes, and please refer to the again the table which is mentioned in the write-up. It's all the shapes and what's when you're doing matrix multiplication, shapes will be very important. So just even for debugging, keep printing your shapes if you face any errors anywhere. So in the forward function, similarly, you will code this particular thing. Yeah, and it's commented out in the code as well that there is this identity thing which helps you to do the matrix multiplication in a better way and helps you to maintain that shapes. So keep an eye on it, because some in the future homeworks as well, and in the future equations as well, this iota thing will come very handy, and this will help you to do the matrix multiplication and summations in a much more intuitive way without using any for loops. So I'll just give you one example of how MLP 0 works. So here, if you see that there is we have defined layers in the as linear 2 comma 3. Why it's 2 comma 3? So here 2 is the input and 3 is the output, and this similar again this you can see in the writer, wherein when you will go through your MLP 0, yeah, your A0 is 2 and you have an output of A1 at you have three outputs at your A1. So so here we have there is 0 hidden layer. So that's why we are just there's an input layer and the output layer, and we have just defined one linear layer in the layers function in the layers. Why have we why have we put it as a list? So that you can scale it for the other versions when you will be writing the code for the MLP1 and MLP4. So you can just keep adding your layers here in the later part of the code. Similarly, F represents your activation functions here, using relu for the first layer. For all these for the other MLPs, as your layers keep increasing. Here we have mentioned what all activation function you have to use for each and every layer. In the for this particular project, you can just use relu functions for all the layers. So how do these connect with the functions you have written in the and then in the separate activation.py files? Let me just write it here. So how will you connect it? You will just call the self.layers first layer here, and you can call the forward function, wherein your input will be to the input for the first layer will be A0. So that will be your input, and this forward function you will already have been implemented in your linear.py file, this forward. So basically what it will does is that it will call the linear layer, and this linear the instance of this linear layer will call the forward function. Similarly, now for A1 you will calculate the activation. So you will call the cell dot 0 dot forward, and where here you will pass the output of the linear layer. So here you will pass the Z0. This way you can do the backward function as well. So here you can, again, using these layers and f, you can connect back and call the backward functions, which we have written independently for every, for the linear layers in your linear.py file. This on exactly similar way, you can extend it to MLP 1, 4, and you should be good to go for with that. Other than this, I would say for the loss functions, we are calculating two types of losses, MSE loss and cross entropy loss. You must again read the write-up. In the write-up, it's mentioned where do we actually use MSE loss and where is cross entropy loss is being used. So basically, cross entropy loss is being used for classification problems, and MSE loss is basically used for regression problems. And for every to-do is being mentioned here, for each and every to-do, you can just fill out with your implementation and look at the write-up for the mathematical part of it. Any questions you guys have? And I would say if there are any personal, like if you are facing any challenges in having, it's like if there is a particular issue with completing the homework, then we can take it personally in the OH. But if it's any open-ended question, I'm happy to take for part 1. Yeah. So no, for this for part 1, you don't require any GPUs, so you can do it in your local. Anything else? One also. If you are good, we can move to part 2.
A pro tip, I would suggest completing the starter notebook of the part 2 first, run it on ablation, and then in parallel, you can start doing a part 1. Because both homeworks have the same deadline, so you need to do a bit of multiprocessing.
Okay, hi everyone. I'm Uni, and this is our thought that we are leading homework 1, part 2 this time. So let's just switch over to slide. So this bootcamp will be basically about like how you can get started with your homework 1, part 2. So let me give like a little overview of this homework. So like it's pretty simple, like to be honest. So the given data will be like speech recordings and a raw Mel spectrogram frames, and the task is to predict the corresponding phenome state labels in the test data set, applying the idea of multi-layer perceptron that we learned during the lecture to train the model. So the basic workflow will look like this, which is also included in your write-up as well. So once you download the dataset from Kaggle, you'll first need to set up so-called dataset class that pre-processes data in a way that we want to feed the model. And subsequently a data loader, which will load the pre-processed data so that it's ready for your model to chug it. Then the fun part begins because where you'll be setting up some hyperparameters for your outlations, and then you will start training and testing the model based on your selections to see which configurations work the best. Yeah, so our data is basically what we started from the raw speech signal, also known as the speech waveform. To convert this into a more useful representation called Mel spectrogram, we apply short time Fourier transform on small overlapping segments of the waveform to separate out all the individual frequencies present in the signal. A single vector is produced after this transform, and the final shape will be 100 vectors per second since we use stride of 10 milliseconds between each frame. The dimension referred as featured picture length will be 27, meaning that we have 27 different extracted features that represent the original waveform. So from the smell spectrogram, what we are trying to predict is phonemes, which is basically the way to represent how our speech sounds like. We have total of 40 phonemes, including SIL, which is like for silence, POSOS, start of which like start of the sentence, and EOS, which represents end of the sentence tags as well. Your job is to train your MLP model that gets to correctly predict phoneme transcript from the smell spectrograms.
So a quick show of hands, how many have completed dataset class in the homework? Okay, 1, 2, 3, 4. All right. So did anyone try working on it and got stuck, or you yet have to start reading the write-up? All right. So I won't go into too much detail because it's probably because you've not tried yet, it might be too easy for you already. We did cover the Libby speech in our first recitation. So you can look at how we made the dataset class there. This has much more components than the simple toy example, but the general idea is the same. You have been given basically 4 different directories. There is a train 100, which is actually 100 hours of recording. Then there is a train 360, which is 360 hours of recording. Then you have a dev dataset for validation, and you have a test dataset. So for any dataset, you just load both the MFCC and transcripts, unless you're working with tests, so you don't have transcripts. And I recommend once you're getting the list of all files that are existing in a folder, you should sort them out, just so you're perfectly matching the same MFCC, the same transcript. Then once you have a list of files available in the directory, you just load them one by one. There's a simple command. You can check the NumPy documentation, and then there's something called substrate normalization, which we discussed yesterday also. Can someone tell what substrate normalization is, or did someone figure out what that normalization was about? Okay, so why do we do substrate normalization?
Define on the write up for
Go ahead.
Make sure that like right up the connection perfectly.
Okay. And were you able to figure out what the single line code would be? Okay, people who completed the write-up, did you implement substrate normalization, or did you go ahead without it? So there are like 4 or 5 people who have done the dataset class. So did anyone do the normalization? Okay, probably not. So again, this has been covered in the write-up. Like there's 1 paragraph on it. I would suggest today, right in the classroom itself, try to figure how it works. If you can't, ask the TAs for help. It's just 1 line code, but it will definitely push your accuracy by like 1 or 2% up. So yes, we'll normalize the data set, and then we'll concatenate the entire data set into a single array. And then there will be something called context, again, which we discussed. We need context. Okay, can someone explain why do we need context? Yeah, go ahead.
Because if we like know the phonemes before it and after it, then we can predict the phonemes similar to like in English language. Like you get it.
Okay. All right, that's good. Okay, that's correct. And how much context have you been experimenting with? Like, what should be a good number for context?
5 and 5 or 4 or 4.
Okay. All right. So yeah, so context is like a hyperparameter. You can keep on increasing it and see around what range you get a good result. Secondly, there was a question on Piazza, which was a good question. That why do we add the padding 0 only at the very beginning and the very end of all the cascaded MFCCs? Right? So every MFCC is a separate recording. So why not have a padding in the beginning and end of every file instead of having padding just at the beginning of the entire folder? So there are 2 ways of doing padding. One is we can pad before concatenation, where we're padding each and every MFCC file individually and then concatenating them. Or the other approach is we can concatenate everything together and just add some padding in the beginning and the end. Any reason why would we prefer one over the other? All right. So each MFCC file, when the recording ends, so before the recording starts, there is silence. So because there is silence already, whether we pad at the end of the file or not won't really make much of a difference, but it will add some complexity to your code. Hence, we are padding only before the first file and after the last file.
Okay, so success in this homework heavily relies on how cleverly you run your evaluations, like along with your.
Yeah, right.
Okay, sorry.
And at the end of the concatenated files, the last four names of each file have context as the next file.
Yeah, so if you're not padding in between files, the last few phonemes can have context as the next file, but the last few phonemes will be silence. And the first few phonemes of the next file will also be silence. So we'll just be having a few frames complete silence. Any other question? Yeah.
Sorry, I didn't understand. Like, do you mean like we don't need padding because each file already started with silence?
So yes, so we are padding with zeros. Silence has a separate value other than zero. But I think silence has a zero.
Silence itself doesn't have.
Okay, so silence will also have a zero value. So if you convert this into integers, you might be starting with zero as silence, a as one, a as one, etc. So yes, we are pretty much padding with silence.
So your frame will automatically then know like silence begins, so that means it's like a new frame. So that's the reason why we don't have it. So if it changes that, different files.
Okay, a quick question. I said silence will have a value zero. Can someone tell why?
Zero intensity.
Yeah, but that's, I would say, too into the I would say detailed side. Like when you're converting this into integer value, why would silence have zero value?
Zero index.
Yeah, exactly. So and why do we have to? Yeah.
But that's the label, right? Like not the.
Yeah, those are the label, but
Yeah, I'm coming to it. So second question is, why do you need to convert these characters into integers first?
So these are just like for your reference, I started with just to show that I have the look like. But this will get converted into integer, so like it will spit out the like label values as an integer value. And then when you really want to like figure out what each integer value represents, like which phoneme, you have to then like switch it back. So it's like dictionary.
But then if we are using label,
Okay, let us ask. Let him continue.
my question was since we're talking about package, it's about the input data, not about the defining data. So silence might have some.
Yeah. So silence can have some values. I have to check exactly what these values would be, but they would probably be most likely be zero.
But if we use label encoding here, wouldn't it learn
So the reason we are not using one-hot encoding is because we already have aligned every MFCC with a phone. So we don't need to have a full one-hot encoding. That's the reason. So we're just converting like every character into an integer value. So instead of having like a one encoding of 40 classes, we have a single value in denoting the index of this dictionary.
Yeah, but if you have that single index value, it might like I learned some spurious patterns which are like it's showing correlation, but it's not exactly causal. That might be an issue. Which one
So yeah, I don't understand the part of this conversation.
So as even professor said that 2 and 3 and 1 and 3 have like more difference.
Yeah.
But essentially they are all the same. It's just a simple label that we are assigning it. So if we use like for phonemes, if we use the index variable into pattern to 1 hot, wouldn't that like affect the performance of the label?
So so far that we have tested, it did not. But I can still, I would probably try a one-hot encoding versus
Okay. right, let's go back. So as I mentioned, success in this homework heavily relies on how you cleverly run your evaluations along with your study groups. So as you might have heard from yesterday's presentation, hyperparameter tuning and ablations are required for improving accuracy, faster conversions, resource constraints, and of course to climb higher up on the ladder in the Kaggle leaderboard. So what I would suggest is in order to do it effectively, it is crucial that you log all your experiments in a very organized fashion so that you can build on your past learning and develop your intuition. I suggest two strategies which I've used both myself last semester. First one is to keep a manual Google Sheet or Excel to keep your parameters, where you should include all hyperparameters and track them in the sheets. So you could also color code information for easy understanding and learning. And note that this is only an example, and you could add other rows like inference, data augmentation, etc. And other method is to do it in a semi-automated fashion by utilizing tools such as weights and biases, which you can find more information from Recitation 0H. You can set config dictionary of your choice and track different metrics that you want to visualize. So I highly recommend you to check the relevant recitation out and start tracking your training using weights and biases. Okay, so some tips when running Ablations is that you should not vary architectures and successive experience by a huge amount. Instead, progressively build on your past experience. So when you want to test out the impact of certain hyperparameter, keep everything the same and just change the value associated with that parameter. If you start changing every parameters, you wouldn't be able to track which parameter brought in which change to your model. So make sure you verify your learnings at each step. And also you want to incorporate some domain knowledge as well into your evaluations to achieve effective training. So for instance, for this homework, we know that we're going to do some phoneme classification. This domain intuition could lead to an idea that context could play a crucial role in training. So you might want to start playing around with different context value in your training as well. So start your work with several simple architectures and find the best parameter combination there. Then start changing your parameter settings to see if there's any improvements.
So we were supposed to talk about the architectures also, but because there have not been enough Kaggle submissions so far, and even the poll we released on Piazza, most like 90% of the class is still probably going through write-up. So what we'll do is once we have seen enough people have crossed the cutoff, we'll release what the actual cutoff was, and we'll also release the architecture for the cutoff. So we will release the architecture for low cutoff, which should be very easy. Once you complete the starter notebook, make your model slightly wider and deeper, and you should cross the low cutoff very easily. And we'll also talk about the medium cutoff. I've seen some submissions on Kaggle have already crossed it. But yeah, high cutoff is something you have to figure out entirely by yourself. You will not really be disclosing it, in the hackathons. Finally, there are some things about the, asking for debugging help. So many Piazza posts have been releasing some issues, but we don't really have a full understanding of what your environment is. Are you running on Windows or Mac or Linux or Collab, etc.? And second is we don't have full information of what you have tried already. So it would be better if you follow, you do some level of debugging yourself, and then share it with us what exactly where exactly you are stuck. So that way we will not be doing all of the debugging for you, because debugging is something you should be learning in this assignment also. And also one last tip: if you are stuck and the errors raised by the PyTorch doesn't make sense, try switching from CUDA to CPU. So the CPU flags are usually more easier to figure out why they are wrong versus figuring out a bug in CUDA version. So yeah, that's all. Any questions about part 2? Yeah.
Essentially, the low cutoff that was for early submission, the 65% is the public score.
It's yeah. So it's a very low cutoff. 65% is very low. Then there will be a low cutoff, medium, high, and you are supposed to cross for any cutoff. Both your public and private should cross the cutoff. So when you're evaluating your final results, let's say 40% of data is public, 60% is private. So we'll normalize it based upon how your performance was in both.
But rest assured, like for this type, this homework, like private and public leaderboard score doesn't really vary much. So like if you pass like those specific cutoff in your public leaderboard, it will probably like cross private leaderboard as well.
So just be like a couple of points I to be established, but yeah, it's highly correlated.
So ideally, if the cutoff is 65, try to aim for 66. That way, your private would also be above 65. So your MFCC files in Dataset have both public and private. And once you submit to Kaggle, we only confirm your public submissions, not private yet. And it's random which lines in your test file were public and which were private.
And you guys cannot see the private score, so always that's the reason why we say like always aim for more than like 1 or 2% higher than the cutoff, so that you can ensure that yourself across that cutoff in the private score as well.
Any other questions? Yeah. Sorry, can you repeat the question again?
Test data that you're provided in Tableau is only the public data.
So the
That's the complete data. It's just that when you submit, like some random 40% of the lines are selected and done.
So you have a test data with MFCCs. You make predictions on those MFCCs, and we evaluate your predictions on Kaggle. So only 40% of the predictions will be evaluated as public. Remaining 60% will be evaluated once the competition is over. Any other question?
If not, we'll switch the session over to hackathon. So like if you have any like private questions, your own questions, just like raise your hand, and TAs will be there to help you out.
Any questions on Zoom?
Thank you.